Hi everyone, this is the lecture video for class 13 of PH 125, and today we're going to be talking about friction. So we wrapped up chapter 5 just before exam 1, and chapter 5 was all about Newton's laws, and we got an introduction to a few forces. Now in chapter 6, we're just going to continue working with Newton's laws, and we're specifically going to look at some more types of forces. So we're going to start off with a little review of Newton's laws and then also the normal force. So remember, the first law told us that an object's velocity is constant unless a net force acts on it. So this was the law that told us that an object at rest tends to stay at rest. Newton's second law told us that the net force acting on an object causes it to have a net acceleration with the relationship F net is equal to mass times net acceleration. Specifically, we always work with our forces in terms of vector components, and it turns out that Newton's law applies individually in both the x and y directions. And so we find that the net force in the x direction is equal to the mass of the object multiplied by the net acceleration in the x direction, where the net force in the x direction is really the sum of the forces acting in the x direction. And then we also know that in the y direction, the net force is equal to the mass of the object times its net acceleration in the y direction, and that net force in the y direction is the sum of all of the components, of all the y components of the forces acting on the object. Okay, and so this was our general problem-solving approach when we had Newton's second laws, and we're going to continue working on this throughout this chapter. So you'll always want to write down that the net force in either the x or y direction is equal to the mass times the acceleration in that direction, and then set that equal to the sum of the components in the particular direction of interest, making sure that you take into account which forces are acting in the positive x or y direction and which forces are acting in the negative x or y direction. Okay, and then we also know Newton's third law, which tells us that for every action there's an equal and opposite reaction. And so mathematically that tells us that if I have object 1 exerting a force F12 on object 2, then object 2 will exert a force minus F12 on object 1. And so in other words, you end up with the force 1,2 is equal to minus the force 2,1. So those forces are equal in magnitude and opposite in direction. Okay, then we talked a little bit about some specific forces. So remember, we talked about weight, Fg, which is the force of gravity. It always pulls downward. So traditionally, that's the minus y hat direction. Force of gravity is always equal to mass times the acceleration due to gravity, so mg. Okay, and then we know we also talked a lot about the normal force. The normal force was the force perpendicular to a surface that kept an object from sinking through the surface. So in other words, it was the force that kind of balanced out the net force acting in the direction perpendicular to a given surface. So over here, I have a flat surface. I have the force of gravity pulling downwards, which I've represented with my green arrow, and then the normal force pointing upwards, which I've represented with a blue arrow. In this specific case, where nothing else is acting on my object, I only have gravity and the normal force. If my object is at rest, so it's not accelerating upwards, then I know that the net force acting in the y direction must be equal to 0, since the net acceleration in the y direction is 0. And so the sum of the forces acting in the y direction must be equal to 0. So if I look at this specific example here, that tells me that the normal force up minus the weight downward must equal 0. In other words, the normal force in this specific case is just exactly equal to the weight mg. Okay, that's something we're going to be using and doing a whole lot throughout the remainder of this chapter, just like we used it quite a bit in chapter 5. Okay, so we're going to be talking about some other common forces. We already know weight and the normal force, and now we're going to talk about a few more. So the first force that we're going to talk about, which is going to be our focus today, is friction. So friction is the force that acts between surfaces in contact, and its resistance to motion. So in other words, it's the force that opposes motion, basically. Okay, then we're also going to talk about the restoring force. So this restoring force is the force that causes a spring to go back to its original shape. So if you compress a spring, it wants to go back to its original shape. If you stretch a spring, it wants to go back to its original shape. And the reason why is because of this restoring force. Okay, next we're going to talk about tension. So tension is just a force that's transmitted along a rope or a string or something like that. And so it's a one-dimensional force, and it just acts always along the direction of the rope or string or whatever. Okay, and then the last type of force we're going to talk about is the centripetal force. This is a force that points towards the center of a circle. All right, so as I mentioned, we're really going to start with frictional forces. So frictional forces are, we've basically been ignoring them throughout the last chapter. There were several problems that said ignoring friction, stuff like that. And so we've been completely ignoring frictional forces, but in reality, friction exists between it exists between every surface. There are ways that we can approximate that friction is not there. There are certain forces that are very smooth, and so there's a low level of friction. But in general, you're always going to have friction whenever you have surfaces in contact. So even if you look at really smooth surfaces, so for example, I have glass over here. I have a close-up view of glass. As you can see, there are really like little bumps at the molecular level, even though we think of glass as being very smooth. Same thing with ice. If you look at ice, this is down to 2 microns here. You can see that the little ice crystals really do form a little bit of a bumpy surface. And plastic as well. So I have another atomic force microscope image of plastic down here, and you can see that the surface really is quite bumpy if you get down to the molecular level. So even though they look like smooth surfaces, there really are little bumps. Okay, and so what happens is when you have surfaces that slide relative to each other, those bumps kind of like stick into the other surface that it's sliding against bumps, if that makes sense. And so those little bumps and irregularities, they like catch on each other as the objects slide across the surface. And so that slows down then the motion. Okay, and this is really what friction is. All right, and so friction we denote with the lowercase f, and it's just the force between surfaces in contact that resists their relative motion. Friction always points in a direction that opposes motion, or if we have an object that's not moving, friction can still be acting on the object. And so in that case, you think about which direction would the object move if friction weren't acting, if it weren't counteracting some other force and keeping an object from moving, and then the friction always acts in the opposite direction. So you want to think, which direction is my object moving, or which direction would it move if there was no friction, and then say, okay, friction must act in the opposite direction of that motion, or we call intended motion when an object isn't moving. Okay. The other thing to know about friction is since it's really the force that's between the surfaces, so the surface of something sliding across another surface, it really always acts parallel then to those surfaces that are in contact. And finally, the last thing to know about friction, which I think makes sense, remember friction is caused by the bumpiness, right, of the two surfaces sliding across each other. And so if you think about pushing down harder onto those little tiny bumps as they slide across the other little tiny bumps on the other surface, you would kind of get more like sticking, right? They would kind of stick together more. And so you get more friction when you have more force pushing the two surfaces together. And so what is the force that pushes the two surfaces together? That is the normal force. And so that tells me that the frictional force is always going to be related to the normal force. Okay, so as I mentioned, friction can act between a surface and an object where that object is moving, and it can also act between a surface and an object when that object is not moving. So we distinguish between those two cases. The case where the object is moving, we call the frictional force kinetic friction. The case where the object is stationary, we call it static friction. So we're going to start our discussion today with kinetic friction. We use the symbol of the little f for friction, and then we use a subscript k to tell us that this is kinetic friction. So in other words, our object is moving relative to the surface that it's sitting on. Okay, and so remember we said that friction is proportional to the force that holds the two surfaces together, and that's the normal force. And so specifically then, kinetic friction is proportional to the normal force with proportionality constant mu k. So mu is this Greek letter that looks kind of like a U with an extra tail on the left-hand side. It's pronounced mu, and this is the coefficient of kinetic friction, which is why there's this little subscript k there. And so a few things about the coefficient of kinetic friction It depends on how bumpy the two surfaces that are in contact are. And so it will depend on both the surface the object is sitting on and also the object itself. And it's also unitless. So we can tell that it should be unitless by looking at this equation that I've defined here, where Fk is equal to mu k times n. So Fk is the force of friction, n is the normal force. So since Fk and n are both forces, they should both have units of newtons, right? And so for this equation to be dimensionally consistent, we must have a unitless value for mu k. Okay, and then before we move on, let's just take a closer look at mu k. So I'll point out a few things. I have a table over here on the right-hand side with a few common values of mu k. So if you have rubber on concrete, mu k is about 0.8. Rubber on wet concrete, the first value is dry, the second value is wet, is 0.25. And so you can see that the coefficient of friction is much higher on dry concrete than wet concrete. This is why you have to be careful when you're driving. So the wet concrete is slipperier, it has a lower coefficient of friction, and so that's why you can like skid out more easily on wet concrete than dry. Okay, something else to notice here is the incredibly low coefficient of friction between bones and the synovial fluid in your joints. And so this is like crazy low. Engineers would love to create a man-made material that has such a low coefficient of friction. It's really hard to get something so slippery. And so this is what keeps your joints working properly and functioning well. So we should all be very grateful for the very low coefficient of friction in our amazing synovial fluid. All right, so now let's do a quick example with kinetic friction. We have a box on a horizontal surface. You give it a push with some applied force in the positive x direction, and that causes it to slide with constant velocity. So that constant velocity, that's going to be a key piece of information here. All right, and we know the coefficient of friction between the box and the table is 0.35, and we want to know what is the magnitude of that applied force. Okay, so to start these friction problems, it's really important to draw a free body diagram. So I'm going to start with my little spot here representing the box. And so then we know immediately the forces acting on the box. We know gravity is always acting straight down. So that's Fg, which we know is equal to mass times acceleration due to gravity. Okay, and that's in the minus y hat direction if we use a traditional coordinate system. So we have x to the right and y pointing up. Okay, next off we can draw in the normal force. So since my box is on a horizontal table, that tells me that the normal force must be pointing straight upwards in the vertical positive y direction. Okay, and next we know that we have an applied force in the positive x direction. That's the thing we're looking for. And finally, we know that we also have friction acting because the coefficient of friction between the table and the box is 0.35. So to determine the direction that the friction is acting, we remember that the box is moving to the right and friction always acts in the direction that opposes motion. So that tells me that friction is going to act to the left. Okay, so Fk is acting to the left. All right, and so then our goal is to find this applied force. To find the applied force, it turns out we're going to have to find the friction. And to find the friction, we have to find the normal force. So basically, we have to find all the forces in this problem. So here we were told that the box is moving with constant velocity, and that tells me that the velocity in the x direction, it's not changing. So in other words, the box has zero net acceleration in the x direction. So let's just make a list of our knowns. Here we know that the mass of the box is 15 kilograms. We also know that the coefficient of kinetic friction is 0.35. And we also know then, remember we said that Vx is constant, and so that told us then that Ax was equal to 0. There's nothing about the box like being lifted, it's in an elevator, there's nothing like that. And so that tells me that the acceleration in the y direction is also 0. Okay, so from here we're really ready to solve this problem. As I mentioned, we have to find friction, which means we have to find the normal force first. So let's start with the normal force. Okay, so since the normal force is acting in the y direction, I'm going to start with the net force in the y direction. Remember, we always want to start by setting that equal to Newton's second law, right? So ma net in the y direction. And we know that the net acceleration in the y direction is 0. So in other words, the sum of the forces acting on the object in the y direction must be equal to 0. So what is that sum of forces acting in the y direction? If I look at my free body diagram, I have the normal force up, so that's plus n, and then I have weight, or mg, down. So that's going to be minus mg. Okay, and so from there, that must be equal to 0, right, since the net force in the y direction is 0. And so we can rearrange and solve for the normal force. That tells me the normal force is just going to be equal to mg, the magnitude of the weight. Okay, so that's the normal force. Now let's look for the kinetic friction. Okay, so how am I going to find kinetic friction? Well, I remember that Fk is just equal to mu k times n. And so we know n, it's just mg, so Fk is just going to be equal to mu k times mg. Okay. All right, so now we're almost there. We're ready to look for the applied force. F applied is now the thing we're looking for, and that's our end goal. So F applied is in the x direction, which tells me we better look at the net force acting in the x direction, which of course is equal to mass times the net acceleration in the x direction. Okay, so remember the velocity in the x direction was 0, so the acceleration was also 0 in the x direction. So our net force acting in the x direction must be 0. In other words, the applied force must be exactly equal and opposite to the force of kinetic friction, right? Because this net force in the x direction is the sum of the forces acting in the x direction. So that's F applied in the positive x direction minus Fk, because Fk is in the negative x direction. Okay, those two things sum to 0. And so that tells me that F applied must just be exactly equal to the force of kinetic friction. And we already know the force of kinetic friction, it's mu k times the weight, mg. Okay, and that is because the weight was equal to the normal force. All right, so now I'm finally ready to plug in some numbers. So mu k we said was 0.35. The mass of the box is 15. As usual, I'm running out of space, and then we have 9.81 meters per second squared for the acceleration due to gravity. And so when I plugged that into my calculator, I found that the applied force, the magnitude of the applied force, was just equal to 52 newtons. Okay, and that would be in the positive x direction. All right, so that's how we go about solving friction types of problems. All right, and so quick question then. If you were to double the mass of the box, what force would be required to keep it moving at constant velocity? Okay, so to solve this problem, we just remember that kinetic friction was equal to the coefficient of kinetic friction times the normal force. And in this specific problem, we found that the normal force was just exactly equal to the weight of the box. Okay, and so if you double the mass, then you double the weight of the box and also the normal force. And because the normal force is proportional to the friction, you would also double the friction. So since you doubled the friction, you would need double the applied force. And so the final answer here would be 104 newtons. Okay, and so thinking back now on this box example that we just did, remember we didn't actually need to know the velocity of the box. We never found that. We never talked about the velocity of the box. And we also never talked about the surface area of the box that was in contact with the table. So this might seem kind of crazy because, you know, the friction is due to the fact that we have these surfaces in contact. So you would think that it would depend on how much of the surface is in contact, right? But it actually turns out that the surface area kind of cancels out. So if you think about the situation on the left-hand side where you have like the large end of the box on the table, the flat end, then you have more bumps, right? Because the surface area is, you have a bigger surface area in contact, but the normal force is spread out over a larger area. In the case on the right-hand side where you have the box and you've stood it up now on its little end, so you have less surface area in contact. Well, in this case, then, you have fewer bumps to overcome, right, because there's less surface area. But now the normal force is really concentrated on this little bit of area, and so it pushes down on it more. And so it turns out that these two effects, they just kind of like balance out and they cancel out. So it's very interesting, but you don't need to know anything about really the shape of your object. All you have to know is the coefficient of friction between your object and the surface. All right, so that's it for kinetic friction. Now let's look at static friction. So static friction, we use the symbol F with a subscript S, and this is just the friction between a surface and a stationary object. If you're sitting at a desk or something, if you have a book or a notebook or something, try just giving it a little light force and see if you can push on it a little bit without it moving. So the fact that you're pushing on it and it's not moving, that is static friction acting against you. So if you start really lightly and then you give it enough force, at some point it will start to slide. And so it turns out that maximum force that you apply, right, as it starts to slide, that corresponds to the maximum value of static friction that can exist between the surface of your table or desk or whatever and the book that you have sitting on the desk that you're trying to slide across it. Okay, so then the maximum frictional force, the maximum static frictional force, it turns out it depends on a new coefficient of friction. This is going to be the coefficient of static friction, μs, and then it still depends on the normal force. So this is just the maximum value that static friction can take on between two surfaces. But if it doesn't need to be that high, it won't be. So it turns out that the frictional force between two surfaces, the static frictional force, it will take on some value between 0 and this maximum value. It will be just the amount that you need to balance out the forces in the direction of motion so that there is no motion, right? So whenever it's static, there's going to be no motion. And so you end up with some frictional force that's something between 0 and this maximum value, which is μs times n. So this is a little bit tricky, and don't worry, we're going to do a good amount of practice with this. So again, a few more properties of μs. Just like the kinetic coefficient of friction, μs is unitless. So it's the proportionality constant between Fs max, which has units of newtons, and the normal force, which also has units of newtons. So μs ends up being unitless. It also depends on how bumpy the two surfaces in contact are. And in general, we find that μs is going to be something bigger than μk. So in other words, that tells you that the maximum force of static friction, it's usually going to be a little bit bigger than the force of kinetic friction right after your object starts to slide. Okay, and I have a table over here. I've just added on an extra column with some coefficient of static friction values. So as you can see, the coefficient of static friction continues to be bigger, or it is bigger than the coefficient of kinetic friction here. Okay, so now we're going to look at a few examples of static friction. So the first example is the force between your shoes and the ground when you're walking. So as you walk, actually, if you think about it, I have this top case here, right? As you swing your foot forward and then place it on the ground, the force that you exert on the ground is actually forward. So it's in the same direction as the direction that you're walking. And so what that means is that the force of static friction, it's going to be in the opposite direction. Your foot's not moving, it's on the ground, right? And so it's static friction, not kinetic. Hopefully you're not slipping and falling down, right? So it should be static friction that's acting, and it's going to oppose the direction of, imminent motion, which would be forward. So static friction acts backward. Okay, then as you shift your weight, there will be a point where you are right over the top of your foot. And so the applied force of your foot on the ground is actually going to be 0. At that moment in time, static friction will also be 0. Then as you start to swing the other leg forward, the original leg that we were talking about, it ends up kind of behind you. And so you end up pushing backwards then with that force. And so then this force of static friction pushes forward on you to keep that foot in place, to keep you from sliding. And so this is how you are able to walk, right? It's because of the friction of the ground. Otherwise, you would just slip and slide all over the place. Okay. The other good example of static friction is when you are driving. It's actually static friction that propels your car forward as you drive. And so when you have freely rolling tires, you end up with a patch that's on the ground, and that little bit of the tire that's on the ground, it's stationary for that moment in time that it's on the ground. And so as the car then pushes backwards, because the tires are they're rolling in a forward direction, so that piece on the bottom is going to be pushing backwards on the ground. And so then the force of static friction is actually the force that propels your car forward. Okay, and so if your car is slipping, so if there is kinetic friction between the car's tires and the ground rather than static friction where you have this rolling action, that's actually when you like skid out. If you've ever hydroplaned or anything like that, it's very scary. It's not a good feeling. So that's actually because you have lost static friction between your car and the road, and it has turned into kinetic friction. And so that is like skidding or slipping instead of rolling is, that's what you want. You want your car to be rolling on the ground, and you want to have this static friction between the car and the road. Okay. So we're going to wrap up today with a quick example, and don't worry, we're going to do more examples like this in class. Like I mentioned, I know that static friction, it seems simple, and then once you get into it, it can be a little tricky. Okay, so first question here, we have a 50 kilogram mass at rest on a table, the horizontal table, and the coefficient of static friction between the table and the box is 0.5. Okay. You apply a horizontal force of 200 newtons in the positive x direction to the box, to the mass, and we want to know what is the direction of friction. Okay, so here, if I think about the box, I like to always start these friction problems with a free body diagram. So here I have a free body diagram of my mass or box on the table, and I know that the applied force is in the positive x direction. And so if there was no friction, then the box would go forward, right? It would go in the positive x direction. And so that tells me that the force of friction, it must be in the opposite direction, so it should be the negative x direction. Okay, next question is what is the normal force on the box? And here we're just going to approximate things, and so you can use the acceleration of gravity. You can just use 10, so don't worry about 9.8, just use 10. Then you can do it in your head. Okay, so what is the normal force? Well, I want to start with the sum of the forces acting in the y direction. Since the box is at rest on the table, that tells me that the net acceleration in the y direction is 0. And so in other words, the sum of all the forces acting on my box must be equal to 0, right? So I have the normal force upwards and I have weight downwards. And so in other words then, the normal force must just be exactly equal to the weight, which is m times g. M is 50 kilograms, G is 10 meters per second squared, approximately, and so I get a normal force of 500 newtons in the upward direction. Okay, so last question here is, does the box move? And just a thought here, remember the box will not move if the frictional force, just like when you were pushing the notebook across the table, so if the frictional force is less than some maximum value, right? So that's when the box will not move. Okay, so let's see how I went about solving this problem. So first of all, I need to calculate the maximum force of friction that's allowed between the box and the table. And so that maximum force is just the static friction coefficient multiplied by the normal force. In the last question, we found out that the normal force was 500 newtons, and so multiplying by 0.5, I find out that the maximum frictional force that can exist between the table and the box is 250 newtons. And so then our goal is to figure out, is the frictional force in this particular case, is it going to be less than or equal to the maximum value? So if it's less than that maximum value, the box won't slide. If it's more than that maximum value, then we really have kinetic friction rather than static friction. So how do I find out if this frictional force F is less than or greater than or equal to this maximum value of 250 newtons? Well, I use my Newton's second law relationship. If the box doesn't move, then that tells me that the net acceleration in the x direction must be equal to 0. And so then that tells me that the net force in the x direction must sum to 0. The forces acting in the x direction are my applied force in the positive x direction minus my force of friction, which I'm just calling F because we're not sure if it's static or kinetic yet. Okay, and so that's acting in the minus x direction. All right, and so then I get F applied minus the force of friction equal to 0. So in other words, In this case, the force of friction must just be exactly equal to the applied force. And so then our goal is to figure out, is this frictional force greater than, less than, or equal to the maximum force? Well, remember my applied force was 200 newtons. So I can see here that 200 newtons is in fact less than the maximum force of static friction that can exist between the box and the surface. And so in this case, the force of static friction in this problem would be exactly equal to the applied force, so it would be 200 newtons, which is less than the maximum value allowed for static friction, and so I would say that no, the box does not move. Okay, so that wraps it up for today. We'll do more practice in class, and I'll see you then.